Positive kinetic energy density. Let me give you an example. Some of you may have already seen this example, actually, and it discussed more or less also. Okay, so now, for me, a ghost will be an object with negative kinetic energy. Let me give you this example here. Okay. I try to find it a quadratic case. Now, as you can see, the kinetic object of this thing has opposite sign to the one that we usually would put. Okay, that for me would be a ghost. Then, when we write down our kinetic matrix after the reduction of the whole degrees of freedom, okay, the determinant will be different from 0. And we have to check whether it is positive definite or not, that matrix. If the matrix will not be positive definite, means that one of the eigenvalues will be negative. At least one will be negative. So there will be a ghost in the system. Okay? All right, so Kij must be positive definite. Okay? And Kj, remember, Kj is the final matrix where the determinant is different from 0. Determinant of Kj is different from 0. Okay, in this case, the determinant of Kij is actually non-zero. So we are in one of these cases. And but now I chose a negative sign. For me, that I will call to be ghost. Now, let's see instead like the Lagrangian of a standard particle, which will be this one. Okay? Maybe k square, right? So k, actually, not k square. Kx, no? I forgot. What is this one? K or k square? Huh? K. So I was right at the beginning. So then we have this kind of matrix. Of course, k is usually we consider positive, okay? Mm-hmm. Okay, so now let's see. You see that, let me call it this one G, okay? So you see that Lg is equal to minus L, okay? The only difference is the overall minus sign.
So what is these are
So this would be the Lagrangian of a standard field, okay?
This one would be
The Lagrangian of a ghost field. Now we see that Lg is equal to minus L. Now, if I consider my Lagrangian equation, you will see because Lg is just differs by sign, these two Lagrangians have the same equations of motion. Okay? So as long as I see the dynamics, they have exactly the same dynamics. No difference. If you give the same initial conditions, that's all. Okay, because the equations of motion are exactly identical.
Every term in the K matrix has to be positive, or just conditions on a determinant.
This is no okay. Once determinant is different from 0, this is not enough. We have also to assume that all the eigenvalues are positive.
All the eigenvalues.
Yeah, which is usually in metrics we say must be positive definite. By this we means that this object here is positive for any xi xj. Of course, when we diagonalize, the eigenvalues are all positive, right? Okay, so then this means that they have exactly the same equations of motion. I cannot distinguish them. They're undistinguishable. But the difference is that this one, if I look for the Hamiltonian will be different in sign. Okay? All right, so the energy of the ghost then seems to be opposite in sign with the energy of the standard particle. Now, the energy of the standard particle is positive definite, because the energy we just have to split minus with plus. Okay? The energy, so this is kinetic minus potential. The total energy will be kinetic plus potential. So the energy here, the H will be in keeping x, so which is positive definite, and bounded from below, but has no bound from above. Now here, but for the ghost, exactly the opposite. For the ghost, the energy is unbounded from below and bounded from above. Okay? So now that now we know that the ghost is a particle with a negative energy. So in special relativity, we will write that the energy of the ghost would be, P mu of the ghost would be minus E P, where E is positive. Okay? E.g. stands for the energy of the ghost. Because the Hamiltonian is negative definite and bounded from above. And actually, this one would be, E.g. would be just the standard one, P squared plus M squared. Because that comes from the equations of motion. So now what happens is that, but for the standard particle here, we would have the opposite. Let me say Q mu, EQ, and Q vector. Okay? Where this EQ is just the standard one, Q squared plus maybe mu squared. They may have, in general, different mass, these two objects. And you see the problem. The problem is the following. The problem is this. So the problem is that I may have this kind of phenomenon in vacuum. So some production of particles and ghosts at the same time from vacuum. And the reason is the energy is conserved. Because the total energy that initially was equal to 0 should be equal to the final energy, which is minus Eg plus, I don't know, here I put 2 standard EQ1 plus EQ2. And conservation momentum would just give me that the 0 momentum, it was equal to K, probably P, plus Q1 plus Q2. But this one is easy to, it just says that they are on a triangle, fine. And this one is always possible. In this, if they were all standard particles, there would be plus here. And these are all positive. So it would be impossible. So if I have only standard particles, vacuum cannot decay. But with a ghost, because its energy is unbounded from below, I can create as many standard particles, just my ghost particle goes more and more down. So kinematically, this process is allowed. Negative energy? Yeah. Yes, of course. If you have some interaction between a system which has very negative energies and the positive energies, then you can have a transfer of energy. The point here, the real difference here, is that this energy does not have any lower bound. If you would have a lower bound, then it would be still okay, because there will be some transfer, and then that's all. After some time, the transfer is over. But here, no, you can go. I can add as many particles as I want here. I can always find some solution for this equation. Okay, so then it looks like that. But of course, here what I am assuming here, that I am assuming one thing, that there is a coupling between the ghost and the particle, and the standard particles. Okay? If there will be no coupling whatsoever, then even though this is allowed, yeah.
In case of Dirac solution, also initially we have negative energy solution. Then of course there is changing P by minus P, that kind of thing, making then energy to be positive, that kind of approach. But still now very similarity is there. And you are telling about this from vacuum, this ghost and the particle. There also we could have particle and
yeah, but for the antiparticle, the energy is still positive. It would be completely wrong to put it as negative energy. That would be boom.
I'm telling
Dirac didn't say that, huh?
No.
Otherwise,
No.
Nobel Prize, I think.
Mathematically, if you go, you actually land into negative energy solution.
Yeah, but
you flip the sign by considering P to go to minus P, and then
yeah, but
in the solution you flip back.
Yeah, but I do the interpretation as an opposite charge solution with positive energy, and that's all. And that's all. But here is a very different way. It's like actually this one is like.
Here it is quadric in momentum also.
So anyhow, so this is okay. Oh, this is a different picture actually here. But anyhow, so what the point clear here?
If you have zero now negative energy, then I can get energy out of it, putting any normal particle through
Exactly.
to the ghost. I will
Yes, that's true. That's exactly the problem of ghost. That's why we will not allow that. Because when we will do this, if there is an eigenvalue which is negative, it's almost sure you will have some coupling between ghost and non-ghost particles. There will be some non-zero kinetic energy which couples them, or maybe some mass term, or this mixed matrix term. So almost for sure that you will have some couplings. And even if you don't have coupling at quadratic order, you may expect that cubic order some coupling will come. So no matter what, that's a really dangerous thing we had to avoid. Okay. All right, so this, notice one thing, notice. If I would have studied the system from the equations of motion point of view, I would not have found any difference. That's how the action becomes important, of the Lagrangian becomes important. Okay? For example, suppose you say that, suppose there is a ghost in the tensor modes. You say, okay, I don't care my structural formation because structural formation is mostly scalar modes. Yes, but we know that non-linearly there will be coupling. So again, we will have, we should expect to have problems there, actually. Notice this is very similar to what we do here, because what I write here, this is the energy of a free particle, right? But when I do this kind of thing, I suppose there is a point at which they do interaction. They do interact, so there is non-trivial interaction there. But far away from this interaction, these become free again particles. So this is when we do this kind of energy momentum conservation, we assume that. So in the same way here, we should avoid the ghost. So automatically we had to say that the no-ghost condition must be verified. The easiest way to verify, once we will find this Kij, we have to diagonalize and check the sign of the diagonal elements. Once we prove that the matrix is positive definite for a choice of variables, then we are safe. Because as I say, this thing must be true for any xi, xj. Okay? The only thing is that when we do a field definition, the only thing we had to make sure is the determinant of this field definition is different from 0. Because otherwise we don't have one-to-one correspondence between the variables here and the variables there. Okay? This matrix must have also determinant different from 0. And what we'll get here, we will get D transpose K D. This will be the new K. Can you see? So this is Kij xi xj. This is nothing but xi Kij xj. And this is X transpose. So I try to be clean. So this is X transpose Kx in terms of, if I write in terms of matrices, right? Now, if I say that X is equal to dy, okay, this will be y transpose d transpose k dy. Now, the new matrix K prime will be the transpose kd. Now I look for my determinant, and this will be determinant of k in general times this determinant of d squared. So as long as this one is different from 0,
complex also
No. These are real variables. All these one are real.
You are assuming. Because otherwise,
And because G alpha beta is a real variable.
okay, for that.
Yeah. Otherwise, we change gravity completely. It would be really modification of gravity. Okay, so then this one will be different from 0, so any value, but then it means that the terminal k prime will have the same sign as the terminal k. Okay? Then as long as the terminal d is different from 0, we are fine that if we show that this one is positive, this one will be positive, for example. Okay, so that's the first thing we had to. Once we write down our Lagrange in this, once we reduce the degrees of freedom, we are fine. Okay. I wanted to give you another example. Yes, I'll give you an example. I don't find it here, actually. Possible. So I had to give you two other examples of Lagrange multipliers. And then hopefully we start the program. If I had time, I hope so. Okay. So let me erase this. Now, maybe you may ask, why in classical mechanics I never care about this? We never care about Gauss condition in classical mechanics, actually. It's because in classical mechanics, we defined the, we have particles. Now we immediately write this one. Which is already positive from the beginning. The only point is that when we have negative mass, okay, but in classical mechanics, the students say, what about the negative mass? The professor will go out of this room, okay? So people usually don't dare even to ask what is a negative mass, okay? Right, so then, because if we have more particles, we would do this one plus these two things, and so forth and so on. So when in classical mechanics, we immediately, by default, do this, actually. The problem in our case, we are not building this action in this way. We introduce this thing. And this is a very complicated object of my fields, actually. We don't know from the beginning whether this one has this form or not, unfortunately. So we had to actually to bring that action in that form.
What about, say, multiplying by overall, say, positive some factor? Lagrangian, say you consider one Lagrangian, then you consider another Lagrangian, which you have basically multiplied by not any negative quantity, but multiplied by positive quantity.
That's fine. So you mean
Motion is same.
You mean this kind of thing?
Yeah, that, so basically the earlier example where you are telling one is varying with respect to the other by overall minus sign. I am telling overall plus sign, but some factor.
Yes. Then the two.
The equation of motion is same.
Exactly. Because the equation of motion will be the same because you have an overall factor.
Right. But energy probably is different.
It's true, but yes. So yes, you're right. You will have. What you're saying is totally correct, actually. What you're saying is totally correct. But the point is that if you have an overall yes. So if you have an overall factor sign, then it's possible to make a Fourier definition such that if it is positive, If it is positive, then it means, so suppose I have this. And then I multiply by alpha. Alpha is positive. Okay, then I define x to be y divided by square root of alpha. Because it's positive, then I get rid of it. I can make a field definition such that I completely remove it. But if it is negative, complex field. And then I cannot do that. So, yeah, I can do that, but that's just up to a field definition, which is completely.
If you don't do that, then of course the energy will be different.
Yeah, but you see, this is a very trivial field definition. I mean, I can always scale by constant anything, actually. The physics should not be changing. That means that the difference of energies will not be changed, the ratio of things will not be changed. This is true even in electromagnetism. I can define FIB, I multiply by 2. Yeah. Okay. So I want to give another example. Maybe other 2 examples, or 3. It's like, yeah, they may multiply a lot, actually. And the reason why I say this, because we will have many of this kind of, yes, maybe, okay, since we are talking about ghost, I want to say another things about, I'll give you another example about ghost, and then we go out of the ghost issue, okay? And we will discuss, again, reduction or degrees of freedom. Okay, now suppose that's something that I said maybe, this one I have the notes. So now suppose that I have something that I said a few lectures ago. Suppose that I have a theory with higher derivatives. So I have 1/2 alpha x double dot square plus beta x dot square minus gamma x square. So notice this is a quadratic Lagrangian, something that in principle we may have. Okay? But again, notice that now I have this double dot here, so we should expect the equations to be 4th order in time. Okay? Now what I want to do, I want to use the constraints and give dynamics to the constraint field, actually. Something that actually you ask me sometimes. Okay, now the trick that I'm going to do now, you have already seen it. In the context, remember that when I discussed the case of general relativity, I told you that R contains second derivatives. So it looks like it's a bad thing like that. But if you remember, R is, yes, contains second derivatives, but it's linear in the second derivatives. So when I multiply by square root of minus g, which is no derivatives, I can do integration by parts of my second derivatives, and I don't have any more second derivatives in the game. Because R is linear in the second derivatives. But remember that I said, what if I take f of R? It looks like now I don't have any more this kind of magic thing, actually. But remember, I introduced a Lagrange multiplier for this theory. And here I have the same thing. X squared, x double dot doesn't come linearly. It's a function. It's a quadratic function. It's like f of x double dot. So I'm going to do exactly the same trick that people use in f of R. 1 alpha, which variables I used now? Y. This will be my f of R, because I say that this one is kind of cousin of R. So this will be the f of R. Plus alpha y x double dot minus y plus beta x dot square minus gamma s square. So what I've done here, I have introduced a Lagrange multiplier because y is a alpha is a constant. Y is a field. Notice y it comes quadratic, quadratic, quadratic. So I'm not destroying the structure of the action. My action is still quadratic in my fields. And y has no derivatives. So it's Lagrange multiplier. Okay? And it's a Lagrange multiplier of the first kind, which means I can integrate it out. It's exactly like in f of r. So the equation of motion for the Lagrange multiplier of y will tell you that this is 0. And this implies 2 alpha y plus alpha x double dot minus y minus 2 alpha y equal to 0.
In second term, you have to put 1 up?
Here,
Yeah.
I don't think so. Because here I had to put the d phi df over the dy. Anyhow, so you see the equations of motion with not 1/2 here, I will get alpha y. Ella, maybe you're right. Hold on. 1/2.
Because then only you go to the previous step, no?
Just a second. F. Okay, you're right. So what I said here that f of x double dot is x double dot square. So then this will be 1/2 y square plus. Okay. This square. Okay. So this will be 1/2 f of phi. This is correct, plus df over d phi, which will be alpha y times x minus y. Yeah, this should be true. Okay, so alpha y plus x. Oh, okay. So this means alpha y x double dot minus alpha y square. Okay? So this means that this is alpha y plus alpha x double dot minus 2 alpha y equal to 0. Okay? Okay, so this means that alpha y is equal to alpha x double dot. So it means that y is equal to x double dot. Okay?
Okay, then from first term, then you have to remove because you are substituting f(x) double dot is equal to 1 up.
No. Hold on. Yes, so my f is this one. Okay? So I write this one. This one is this, and you get this.
Achha, your f is like,
Okay? Now, when you take a derivative, you get this equation. This equation of motion says that y is equal to x double dot. Now, this constraint is not a differential equation for y. It's an algebraic equation for y. I set it inside my equation. This vanishes, and you get 1/2 f x double dot. So the meaning here is that these two Lagrangian will have same equations of motion. Okay? This is one of the equations of motion. The other equation of motion is when we find the equations of motion, and we will get the same one. Should I check it? Let's do it. No? Let's do it. So, okay, so let me find the equations of motion for this action here, actually, in terms of y. So this we will get two derivatives of this guy, alpha y double dot, with a plus sign because I integrate by parts twice. Okay? Then I will have minus beta x double dot, probably, because I had twice beta x dot integrated by parts. I get minus 2 beta x double dot. And then I will have minus 2 gamma x equal to 0. But y is equal to x double dot. So here I will have alpha x 4 dots. Okay? That's exactly the same equation that I would get here. So the two equations are equivalent because they lead to the same equations of motion.
So the constraint has taken care of the ghost.
Not yet. No, at the moment I have used the Lagrange multiplier such that my equation now they don't have any more higher derivative terms. They disappear. I only have at most second order terms. It looks like, whoa, so then it's good. Then I fix the problem. And now I'll show you in our formalism what happens. Okay? It looks like the higher derivative theory has disappeared, leading to a theory which is only second order differential equation, which is true. The equations of motion here is second order, and the equation of motion here is second order. It seems everything seems to be fine. But let's see what happens. I can make integration by parts. I will get minus x dot alpha x dot y dot. Okay? Plus beta x dot square minus gamma x square plus 1/2 alpha y square. Sorry, but I had also this alpha y here. So actually this becomes minus. Okay? Because I had the minus alpha y square plus 1/2 alpha y square. So overall, I get a minus. Okay, so up to a simple integration by parts, these two actions are, again, same. Okay? But now, look, I have a kinetic term for y. My kinetic matrix looks like this. Let's see if I get it right. Beta minus alpha divided by 2 minus alpha divided by 2, 0. This is my kinetic matrix. The determinant is different from 0. I stop here because I have found a system for which the Kij has non-zero determinant. But determinant is positive or negative? It's negative. And that means that I will have one ghost. The determinant of this object is this times this minus this times that, no? So it will be minus alpha square square, which is minus alpha square divided by 4. Okay? So no matter what's the sign of alpha, the determinant is negative definite. What does it mean? It means that if I diagonalize this matrix, I will have one positive, one negative. Okay? So indeed, higher derivative theories if we will find in our perturbation something like this, we should really worry about it. Because in general, we will have ghosts. So if I have phi double dot square, this in general will lead to ghosts. Okay. Now, let me show you, and again, I'm losing time, but I think it's maybe useful. Now, okay, we have this 2 degrees of freedom thing, and I want to diagonalize, okay? And I want to diagonalize in the probably simplest possible means I may have, okay? So I had to do a Fourier definition, because in this basis, x and y, they are not diagonal. So I had to change basis. So I had to do like xy is equal to a 2 times 2 matrix, q1, q2. Okay? And the way I do it is the following. Hopefully, it should work. 1, 1, 0, and I put here parameter alpha, beta, gamma, delta, epsilon, lambda. Okay? The way I choose this is because the determinant of this matrix is 1. So this transformation is always well defined. Okay? As long as lambda remains finite, let me put it this way at least. So this means x is equal to q1, and y is equal to lambda q1 plus q2. Okay? Let's see if we can diagonalize with this one. And can we diagonalize this one? Yes, we can, because we have one. This matrix is symmetric, right? Will be always symmetric. Kinetic matrix is always symmetric. So the non-diagonal part is only 1. So one equation for one unknown, it should be possible to diagonalize. And this structure remains true even if you have n times n matrices. You can do this the same. You have these triangle matrices with 1, 1, 1, 1, 1, zeros, and other variables here. The number of the constraint will be equal to the number of the unknowns you have. Yes, so this is 2 times 2 matrix. When I do a change of basis, the new kinetic matrix will still be a 2 times 2 matrix, which is symmetric. And we want to set to 0 the non-diagonal term, which is only 1, because the matrix is symmetric. And we have one unknown, lambda. So it should be possible, one equation, one unknown, to diagonalize. Okay, so let's do the calculation. How do we choose this matrix? You put as many unknowns. Suppose I have a 3 times 3 matrix. No, you will put 1, 1, 1, 0, 0, 0, lambda 1, lambda 2, lambda 3. If you have 3 times 3 kinetic matrix that you want to diagonalize.
It's also not clear why the diagonal elements, why are they 1?
Right, okay, let me put it this way. I want to diagonalize the matrix the most simple way that I know. Okay? I make a choice of diagonalization. I could find the eigenvalues and stuff. Usually the eigenvalues problem is more complicated. Usually it's more complicated. This is simple because you will see this equation will be linear in lambda.
So basically, if you can claim that one of the bases need not be changed, it is, I think, linked with that one of the bases need not be changed.
Only one. For if you have more than two fields, one will not change and the other one. Notice that you can do also this trick. That will be exactly the same. And the other point why I chose 1, 1, 1 this is because this matrix will be determinant 1 from the beginning. So it's simple enough and always works. Okay, now let's see how we get this one. Let me go there. Okay, so we will see then. So then x dot is q1 dot, and y dot is, let me suppose lambda is a constant, because anyhow we don't have time derivatives there. So lambda x dot, so lambda q1 dot plus q2 dot. Okay? And then I had to write down the Lagrangian, which is minus alpha x dot, which is q1 dot, times y dot, lambda q1 dot plus q2 dot. Let's screw up. Ah, yes, plus, of course I have another term, otherwise it doesn't work, plus this one for the derivatives. Plus beta x dot square, so q1 dot square. This doesn't help. Okay, then I change this one, 0 lambda. Sorry, so then I put plus lambda q2 dot, and this will be q2 dot. Hopefully this should work. Okay, so minus alpha x dot, so q1 dot plus lambda q2 dot, plus times q2 dot minus plus beta q1 dot square plus lambda square q2 dot square plus 2 lambda q1 dot q2 dot. Okay, so this was alpha q1 dot plus lambda q2 dot times q2 dot plus beta x1 square. What I care now is the mixed term. So the term in q1 and q2 dot. So this is alpha plus 2 lambda beta times q1 dot q2 dot. Okay? One solution, linear, exists. Because that's the term that I have to set to 0, right? The mixed term. So solution always exists. It's unique because the equation is linear, and we get minus alpha divided by 2 beta.
Minus alpha plus 2. The first equation is minus alpha.
Okay, so we get this lambda here. So this means that this will diagonalize. Okay? And see what we get now. Okay, so lambda, okay, so lambda is equal to alpha divided by 2 beta. There was a dot here. So let's now find the terms which are the diagonal term. The non-diagonal term now is 0. Let's find the diagonal terms. So the q1 square will get this one term here will be beta q1 dot square. Okay, because this one doesn't have any q1 square. And then let's see the terms in q dot square plus q dot square, which multiplies. Here we have a minus alpha lambda plus lambda square beta. Okay? If you say yes, I agree with you. All right? So then this this implies that beta is positive. Okay, let's say beta q1 dot square. And then we had to replace what is our value for alpha. Alpha was alpha divided by 2 beta. So I had to put alpha times lambda, which means that this becomes alpha squared divided by 2 beta minus. And this becomes alpha squared divided by 4 beta. So I will get overall minus alpha divided by 4 alpha squared divided by 4 beta. Okay? And now you see, no matter what, so if beta is positive, this one will be negative. If beta is negative, it will be positive, but this will become negative. One of the two particles is always a ghost, no matter what we do. Okay? Okay. Yes. And then I don't write the remaining part of the Lagrangian because I only was caring about the ghost condition. And now I know that no matter what I do, one of the two particles will be ghost. No matter what value of, in this case, no matter what value of beta I chose, one of the two will always be negative. So no way. This is like a no way thing, actually. No matter what beta, what were my parameters, I have always this problem, actually. So that's why we have as much as possible to avoid this kind of situation. If we cannot avoid, our theory in general will have a ghost. And if you are the first person who found this, you can write a paper. This theory has a ghost. Hopefully the calculations are correct, okay? I want to give you, now, notice that again I have used these Lagrange multipliers. So Lagrange multipliers, and in this case the Lagrange multipliers actually are quite dynamic because they were coupled to second derivatives of the fields. Now, so what I want to do now is to still use Lagrange multipliers in order to reduce degrees of freedom. Now, we use here Lagrange multipliers not to reduce the degrees of freedom, actually. Here it looks like I have only one degree of freedom, one scalar degree of freedom, which was x, but with 4 derivatives. So these Lagrange multipliers helped us to construct a theory which is for second order, kinetic term, one of them is negative. Okay? And we then name this thing, okay, this theory has a ghost. So it was useful in this sense. Okay? No, also this theory had a ghost. It's not that this Lagrangian introduced a ghost. This Lagrangian here was useful to explicitly show there is a ghost. Okay? But the Lagrangian were equivalent. So if one has a ghost, the other one has a ghost. Okay. So it's possible that okay. So tomorrow morning, I will. So tomorrow morning is the day after tomorrow is the last day of classes. Okay. So probably tomorrow morning, I will be able to. We will go to the tomorrow morning as soon as we start. We go there. We see the Maple code. Okay. But before doing that, I have to say more about the reduction of degrees of freedom, because otherwise tomorrow we don't understand anything. Okay, so the other example that I want to do, it's another simple example. How do I write this one? Yes, I have it. Good. So, okay, so suppose I have this action here. Okay? So we have a quadratic action for the fields x, y, z. Okay, x, y, z are fields, okay, are not coordinates, okay, are fields for me. And a is a constant, omega is a constant, and b is a constant. Okay? Now we know that there is a Lagrange multiplier because my kinetic energy, IAJ, does not have any z dot square. So in this matrix here of the derivative, I will have something, and then 0, 0, 0, 0 for the z variable, z dot variable. There is no z dot square, there is no z dot. And this is a Lagrange multiplier of what kind? Second kind, because comes linearly only. There is no quadratic term for it. Then its equation of motion sets a constraints on the other fields. Okay? So the equation of motion for zeta, which is this one, says that alpha x plus y equal to 0. That's the constraints that fix. Now, this is a nice constraint because somehow it's not a differential equation. It's actually an algebraic equation, both for x or y. So we can solve for the variable we like the most. For example, I think in my notes, I solve for the variable y. Y is equal to minus ax. Now, you may say, OK, you solve for the variable y. Is there a deep meaning? Could I solve for the variable x? Yes, you could. OK? And this gives us an interesting kind of a lesson. At the end of the day, people may may end up with different fields. So for example, I decide to solve this equation in terms of y. But somebody else would have said, no, I prefer to do this. This is true because this is still an algebraic equation for x. So I can do it. Okay? And then, so which one is correct? Both. But of course, there will be a difference. At the end, one will be written in terms of the field x, and for the other one, for the field y. But, and this is a crucial point, but for example, the Gauss condition cannot be changed. And the reason why the Gauss condition don't change is for the same reason that when we do this diagonalization, if the kinetic matrix is positive definite, no matter what Kij, Xi, Xj, this should be positive. So no matter which field we use, which field definition we use, the kinetic matrix will always be positive definite. So this is something like a relief, because there is not only one single possibility to study the no-Gauss condition. Okay? If that would be the case, it would be a huge, immense problem. Because every time you had to say, which is my fundamental field? We said, no, the Gauss condition don't depend on that. So I can choose x or y independently. I should have the same no-Gauss condition. sometimes but sometimes life is a bit more complicated than that. Maybe after this one, you see, I introduce an example. I think another example afterwards. That's a problem of this. There is an instability in the number of examples here. Okay, so but hopefully it's not a Gaussian instability. Okay, so then let me suppose I chose this y is equal to minus ax. Okay, then because it's an algebraic equation, I can write it. I can substitute its equation inside its solution inside the Lagrangian, and we have x dot square divided by 2 plus y. So we have a square x dot square divided by 2. And then you see something here. If I put y is equal to minus ax, this one completely disappears. Z goes away. So notice that when we have a Lagrange multipliers of the first kind, we get rid of two fields at the same time. We get rid of y, or of the second class. Sorry, we get rid of two fields at the same time, because we get rid of y, because now y becomes a function of x, and automatically we get rid of z. Instead, when we have a Lagrange multiplier of the first kind, we only solve for the Lagrange multiplier itself. So we remove one field. So a Lagrange multiplier of the second kind is very efficient at removing degrees of freedom. So hopefully one should get many of them. Okay. Okay. So then we write this, and then minus omega squared divided by 2x squared plus b, and then x dot y dot, which is minus a x dot. Okay, hopefully I didn't do mistakes. Okay, so then now I have a single variable x. So let me find its kinetic term. This will be 1/2 plus a squared divided by 2 minus ab Is it correct, this stuff? Does it make sense? You say yes? Okay, I trust you. All right, so x dot square minus omega square x square divided by 2. And I think there are no other terms. Okay? And now we can read immediately what is the no-ghost condition. In order to have no ghost, this quantity must be positive, which is not always true. This is not a perfect square because this is not b square. So in particular, we can solve this equation for b because solving this equation for b is linear. So we find that, say, 1/2 plus a squared divided by 2 minus ab must be positive. So b must be less than if, okay, then we had to solve, okay, so if a is positive, then it becomes b must be less than 1 plus a squared divided by 2a. Probably, huh? Somebody says yes? You say yes? No? Nobody says yes? Okay. So if a is negative, and then we will have b must be greater than 1 plus a squared divided by 2a. Okay? Okay, so we have this no-ghost condition. That from the beginning, it was not completely clear, actually, right? That's the whole point. from the beginning, this one, it was not clear that we had to satisfy these constraints at all, actually. Okay? All right. Now, I want to give you another example, which is much more complicated, but I had to. Remember that the Lagrange multiplier of the first kind are, we can always use them to remove degrees of freedom. Second kind, not always. Now I'll show you an example where we cannot. So this one is clear so far? Okay. All right. So which way I want to do it? I'm sorry, sometimes I am slow. Okay. So I have two methods to solve the same problem, and I don't know which one is best for you. Okay, I should have thought about it before. But okay, so let me try at least this one. Let me try at least this one. Okay, let me try this one. So suppose I have this Lagrangian here, which is x dot squared divided by 2 plus y dot squared divided by 2 minus omega squared divided by 2, x squared plus y squared. So this would be like two harmonic oscillators which are decoupled from each other, actually. And now we put some constraints. We put this constraint here, z a x dot plus c y dot plus y. That's all. So z is Lagrange multiplier of the second kind. We say, hey, great. So then now we can solve for two fields at the same time. The problem is that when we solve this one, you notice that the solution is ax dot plus cy dot plus y equal to 0. And then we have a problem, because this is a purely differential equation. I cannot solve for y. Because for y, I have y and y dot. And for x, I have x dot. So now the simple thing breaks down here. Okay? And then how do we do this? I'll show you this method here. So the way we do this, actually, is the following. We will try to kill, we'll insert an extra constraint to kill, to make either x or y a Lagrange multiplier. Whoa, that's very cool stuff, actually. Okay, so you see that there is no way, right? If I keep these variables, there is no way I can go on. I had to keep z. So the only thing that I can do is field redefinitions stuff. So, and you see that if somehow I am able to remove, say, to get rid of x dot square, then maybe I find something interesting. So the way I do is I take the same Lagrangian and I add this term. minus 1/2 alpha x dot plus beta z minus q squared.
Can't you just eliminate x dot or y dot from that equation?
Absolutely not. That would be a tremendous, huge mistake. If you do it, you lose degrees of freedom like crazy. Let me give, never do it. You will get wrong result. Okay, for example, let me give you the example I wrote before. Okay? All right? Remember, this was an example I gave you before. Okay, so then let me do the following thing. Let me integrate this by parts. I will get minus 2x dot y minus b squared x. So you notice this is of the second kind. I set x dot equal to 0. I replace this into the equation. I get L is equal to minus b squared x. What is that? That's nothing. That's not even degrees of freedom. The solution for this will give you x is equal to 0, which is completely wrong. Remember that our solution was x was equal to constant, and y was constant plus velocity times t. And we get completely wrong answers. Why? Because I inserted not an algebraic equation into my Lagrangian. Bonk. Just to show you, never, ever, ever do that. Okay? All right. So this is quite brutal mistake. So never, ever do this. And that's why the Lagrange multiplier must be taken with care. Only algebraic equation can be inserted into the Lagrange. Actually, it was a good question because I showed that this, if we do this trick here, we put it like this one, brutally like this, we get this one, x is equal to 0. We get the wrong. This is this Lagrangian here is not equivalent to this one because they have different solutions. It's clear that this Lagrangian will set x dot to be 0, so x is equal to 0. That's my, sorry, x is equal to constant, not equal to 0. But if I insert this one brutally into the Lagrangian, the only solution I have, x is equal to constant. Constant, which is only 0. Okay, so no. That's exactly this kind of problem here. In this case, how did I do it? Well, I did the other way around. I knew that x was a Lagrange multiplier of the first kind. I can always solve for it. That's how I solved that problem into this form. By doing exactly the opposite. So this was 2x y dot minus b squared like this. Now x is Lagrange multiplier of the first kind. I can always solve algebraically for it. In fact, I was getting the same solutions. Okay, so as I was saying, in order to get rid of these problems that sometimes happen with Lagrange multiplier of the second kind, I add this quantity here, where you notice I have x dot, z, and q. Q is a new field. I am introducing a new field, which is Lagrange multiplier because it doesn't have any kinetic term. So it looks like I am complicating this stuff. Okay, but let's look at the equations of motion for the. But this comes non-linearly, no? Because you have a q square. So this is a Lagrange multiplier of the first kind. I can always solve for it algebraically. So this will become, let's say, minus alpha x dot plus bz minus q times minus 1 equal to 0. Very simple. Again, this is the f over trick. If you will see it, this is the f over trick. So then q is equal to this thing. You put it in, you insert that one, you get 0. Okay? So I added 0, which is always a consistent thing to do. Okay? But I have a free parameter alpha, which gives me x dot square. And I can choose any alpha, right? And then maybe I can choose the alpha such that I can remove x dot square. Hula. Why don't I see people doing this?
It's not actual. So here Q introduced in a way that it's a Lagrange multiplier. It's not a degrees of freedom.
It's true. But what I'm saying is that I have added 0, no? I proved that I have added 0. So this Lagrange is exactly equivalent to the previous one. So then now, this was a free parameter in this Lagrange multiplier. Now I expand the square because this Lagrange is completely equivalent to the previous one. Okay, so let me do that. I will get 1/2 minus alpha squared divided by 2 So notice here that I had to put the z variable there, times x dot square plus y dot square will not change. This term will not change. At least I leave it like this. And then let's see what we get. Then let me consider the term x dot z. I will have a zx dot, which multiplies a minus alpha beta. Okay? Z dot plus z, which multiplies cy dot plus y. And then I have the square coming from these two terms here. We'll have a minus 1/2 beta square zeta square minus q squared divided by 2. And then I have these cross terms here, which is plus alpha x dot q plus beta zq. Okay? All right? You know, I had to now to bring the action in a way that I know how to do it. And I had to remove all the possible Lagrange multipliers. I introduced an extra Lagrange multiplier. So now I have 2 Lagrange multipliers. But you see what I will do now. I will set this one to be 0. And I will set this one to be 0. This happens for alpha is equal to 1. And beta is equal to a. Because those were free parameters. Okay? And by doing, does it make sense? I had complete freedom to choose alpha and beta as I wanted, because anyhow, this was always 0 on the equations of motion for Q. Then I expand, and now this one will disappear, and this one will disappear. Let's read. Let's see this action what it became. Now the Lagrange now has become. Okay, sorry, I said alpha to be 1 and beta is equal to a. So this becomes 1. This becomes a. This becomes a squared. And that's all. Okay? So we have this term here. You notice that there is no z dot term. So z is still a Lagrange multiplier. But now it has become of the first kind. So it can be integrated out. And let's see what happened to x. X comes here and here. Now, x is not a Lagrange multiplier, but I can integrate by parts this one immediately.
What if alpha equals to -1?
Huh?
Alpha can be
No, remember that this one was alpha squared. We had 1 minus alpha squared. Anyhow, my point is to remove the term, right? I mean, it's not that I want to keep it x as a degree of freedom. It would be bit. Why you would do that? Then you cannot solve the problem. Instead, you want to create as much as, in this case, first Lagrange multiplier of the first kind. That's exactly why I chose alpha to be 1. So this becomes minus q dot x. So x, also x, is a Lagrange multiplier of the first kind. So then x is a Lagrange multiplier of the first kind. Z is a Lagrange multiplier of the first kind. I can get rid of both of them. At the end, I will have q and y. Notice that q doesn't have any kinetic term so far. Y has it, no? We have y dot square. Q, we don't have any q dot square. True. But I have q dot here and x squared. When we will solve for x, automatically we will get the kinetic term for q. Okay, so let's do it. So let me just check that what I wrote makes sense or not. Minus f squared minus q squared minus x q dot plus aq. That's correct. All right, so then let's find 0 is, let's find the constraint for x. This becomes minus omega square x minus q dot equal to 0. So this is solved for x is equal to minus q dot divided by omega square. Okay. Then the other equation is dl over dz, because that's the other equation that I have. Then I will have cy dot plus y minus a squared z plus aq equal to 0. Okay? Yes. All right. So then we can solve immediately for both variables because this one says that z is equal to cy dot plus y plus aq divided by a squared. Okay? Right, so I have those two algebraic equations. I put that back into the action. All right. Okay, so then I showed you how, in the case of a Lagrange multiplier of the second kind that cannot be easily integrated out, what is the technique one has to introduce? You have to introduce a square inside with Q, and making sure you can remove the x dot terms, all the terms that comes in x dot, square, and linear. And then we have that. Okay, so then by replacing this one into the action, you will have something like, hopefully my calculations are correct. So, okay, here I have to put x squared, which means q dot square divided omega to the fourth. And now you see that integrating out qx will give us a kinetic term for q. And then it looks like my actual system was a system with two scalar degrees of freedom. But now we know, because we have the explicit form of the kinetic matrix and so forth and so on. And we have no more Lagrange multipliers. Then we have minus omega squared divided by 2y squared plus, probably this is c y dot plus y plus a q squared. The reason I say this one is because you see the term linear in Z has this one plus this one, right? So you put AQ inside this parenthesis, okay? So you can put this AQ inside here. And notice that Z would be then the square divided by A square, okay? So in other words, I can remove this one here, and I put it plus AQ. And you will see that when I replace Z, I will get the square. And then I have also the term which is 1/2 a squared divided times z squared, cy dot plus y plus aq squared. And then we'll have minus q squared divided by 2 plus q dot squared divided by omega squared. And that comes from the term x q dot. And x was minus q dot. Okay. So since now we want to discuss only the kinetic term, so let's see. This one will be 1/2. Now let's go. Let's get all the y dot squared plus. So notice that this one becomes 2. So we get 1 minus 1/2. So this simplifies into 2 and nothing there, actually. Okay? So notice that this is half of this quantity. Right? So this becomes 2, and this term disappears. Okay? Okay, so then I will get the plus c squared divided by 2a squared, and y dot squared doesn't have anything else. Now let's see what happens to the q dot square. Now you see that we get a 2 here. This simplifies. We have minus 1/2 q dot square, but we have plus. So this was looking like a ghost, but actually we have the plus here. So we have plus q dot square divided by 2 omega square. And you notice that we don't have any cross term q dot y dot. So the Lagrange matrix is actually diagonal, and the ghost conditions are always satisfied, because this quantity is always positive definite, and this quantity is always positive definite. Okay? So that action doesn't have any ghost. which is not exactly clear from that picture there. That's exactly what we want to do, okay? We simplify it as much as possible because we cannot do anything else. Now the kinetic matrix does not have zero determinant, so that means that we don't have any extra Lagrange multiplier. So we cannot simplify further. At most, we can just change variable, maybe to diagonalize something. That's the most we can do now. Okay. All right. I think today probably is over. So tomorrow morning, the first thing we do is to see the code. Okay, because tomorrow I will need time to see the code, and the code is important. Because now all this one looks like example which, made up example out of nothing, actually. But this actually, we will see that we have a Lagrange multiplier of the first kind, the second kind, and so forth and so on. That we need to know how to solve the constraint until we will find the final reduced Lagrangian. Okay.